The 1993 extreme floods in Arizona resulted in loss of life, injuries, and over $400 million in damages. Widespread excessive floods forced several dams to utilize emergency spillways, contributing to already engorged river flows and damage to property in the floodplain. The 1993 atmospheric river-related floods revealed flood control strengths and weaknesses statewide and initiated unprecedented flood-related research. The significance of the 1993 floods is apparent in this figure, which shows the widespread 1993 flooding across Arizona as the black raindrops, comparable overall to the 100-year flood volumes shown as the light gray raindrops. The Salt River Basin and Verde River Basin are represented by the two gauges northeast of Phoenix and were capable of producing large volumes of runoff due to large contributing basin areas adjacent to a regional topographic high, the Mogollon Rim. This video will first focus on the atmospheric river origins and pathways that can penetrate inland to Arizona, and the general hydrologic processes of atmospheric river events in order to 1. Better understand the significance of atmospheric river events in Arizona, and 2. Ultimately provide context for the 1993 atmospheric river event. We will then focus on the hydrometeorological evolution of the 1993 event. Atmospheric rivers are long and narrow filamentary water vapor fluxes responsible for about 90% of low-level meridional water vapor transport in the atmosphere. Generally thousands of kilometers long and 40 to 60 kilometers wide. ARs show integrated water vapor amounts above 2 cm in the lowest 2.5 kilometers of the atmosphere. Atmospheric rivers that affect Arizona primarily cross the Baja California Peninsula south of the mountains on the northern peninsula, or through a gap in the mountains at the California-Mexico border, to then impinge on the Mogollon Rim, which rises approximately 2,400 meters above sea level. The pathway south of the Baja Mountains at the 950 millibar level has an only 8% occurrence compared to other AR trajectories. However, of these occurrences, it does have the highest inland penetrating percentage, at approximately 52%. ARs primarily occur in the cold season, October through March, and show a relationship between precipitation, snow water equivalent, soil moisture, and stream flow response. Although the monsoon season from July to September provides up to 50% of annual rainfall, the majority of this precipitation is lost by evapotranspiration due to high solar radiation, which increases the latent heat flux and evaporative function. Winter precipitation, on the other hand, is not as easily lost back to the atmosphere by evapotranspiration, which can allow for more soil moisture, recharge, accumulation of snow at higher latitudes, and also is associated with higher stream flows than during the monsoon events. ARs increase the percentage of cool season, November to April precipitation, and snow, and therefore are a significant contribution to the hydrology of Arizona. This figure shows the contribution of ARs to total winter precipitation ranging from 0 to 60%, with an average contribution between 25 and 29% for two basins along the physiographic transition zone, the Salt River Basin and the Verde River Basin. The significance of AR contribution to total winter precipitation in the winter of 1993 is apparent in these two basins, comprising 59% and 61% of precipitation. In comparison, most years in the period of study have significantly less AR contribution to total winter precipitation. The 2005 AR event also produced widespread flooding in Arizona, though not as extreme as the 1993 event. In addition to the significant impact on total winter precipitation, ARs contribute to the hydrologic extremes of daily precipitation, with increasing contributions for median, heavy, very heavy, and extreme rainfall. Contributions for extreme rainfall are as high as 64 and 72%. AR events can rise the mean temperature, which effectively can rise the snow melting line to higher elevations than normal, which can contribute larger basin areas to runoff generation. Runoff generation is also enhanced due to increased soil moisture following previous AR events. This figure shows a composite of soil moisture change as a result of AR events. The 1993 AR events caused extreme precipitation due to 6 ARs in a period of a little over a month beginning on January 1st, with durations ranging from 2 to 3 days. This figure shows the evolution of the atmospheric conditions at the 500 millibar height during the AR events that led to the 1993 floods. In January, the presence of a persistent upper air circulation high-pressure ridge in the Alaska region, coupled with a low-pressure trough to the south, displaced typical vapor transport pathways to lower latitudes. The first January storm was preceded by low temperatures and precipitation, which lowered the freezing level elevation and increased snow accumulation at higher elevations. These preceding conditions amplified the resulting floods of the 3-day heavy precipitation event as the warm temperatures and rain on snow virtually eliminated the snowpack and contributed to runoff. The trough was still present following this AR event, and so after the snowpack melted, heavy precipitation continued to fall, which ultimately led to January events producing the largest flooding episodes in 1993 and in recent history. In February, an upper air ridge, known as an omega block, formed over the Alaska region, which prolonged the trough pattern in mid-latitudes and maintained conditions to force ARs on a more southerly trajectory towards Arizona. These conditions were then followed by a cold front as the trough passed through. The upper tropospheric conditions aided the AR trajectory to the Baja California Peninsula, which is a key region allowing for ARs to penetrate inland to Arizona. An analysis of AR characteristics shows the AR itself was strong with an integrated water vapor core between 3 to 4 centimeters, oriented directly toward Arizona through the Baja Peninsula. This figure shows integrated water vapor transport with intensities reaching up to 450 kilogram meter seconds right into Arizona, which is comparable, actually, to strong air events in California. Low-level maximum horizontal water vapor flux is primarily between 116 degrees and 120 degrees west, with intensities from the 600 millibars down to the surface, as shown in this cross-section L1. And then cross-section L2 shows maximum horizontal water vapor flux directed toward the central highlands of Arizona, allowing the orographic effects to intensify the precipitation. An anomalous high-pressure zone in the southern Baja Peninsula is shown on the 500 millibar geospatial height anomaly field and allows for southwesterly flow into Arizona. Orographic forcing at the mesoscale is the dominant reason for excessive precipitation, as evidenced by the very weak synoptic scale vertical motion, as shown by the Q vector convergence in this figure. Lastly, the 300K surface shows the strongest vertical motion is off the coast of California, which allows for the weak ascent of moist air over Arizona. Although the 1993 AR events are anomalous, they had significant societal impacts, and thus understanding their relevance compared to other AR events, hydrologic impacts, and evolution will continue to be of importance. These floods caused damage, loss of life, and were the first to test several dams constructed across the state with unprecedented volumes on the 100-year flood magnitudes, forced the use of emergency dam spillways, and revealed some weaknesses with flood mitigation planning. In addition to the flood risk implications of ARs, AR events provide a significant contribution to Arizona water resources by allowing for more groundwater recharge than monsoons due to decreased solar radiation and evapotranspiration. Extreme AR frequency and intensity has been shown in climate models to increase due to climate change, which poses an increased risk of AR-related flooding. Therefore, it is critical to improve understanding of the role in ARs to past winter floods and their role in future water resources, as they will continue to have a major societal impact on the semi-arid region.